Welcome to part 2 of dynamic programming, one of the most important concepts, but rather simple for us as programmers to learn and really utilize. So I'm going to start by just doing a little bit of refresher, and then we're going to dig into some pretty cool problems. The first thing I want to do is really narrow down the 5 steps to actually doing or using DP. So we're going to do step 1, step 2, step 3, step 4, and step 5. Now, these are incredibly important to remember because at any point when you're really stuck about how to actually apply dynamic programming, look at these 5 easy steps and try to determine where you are in the series of steps to complete this. So the first thing that you want to do is define your subproblems. So if you remember in the Fibonacci sequence example, the subproblem was really calculating a Fibonacci number at a certain place, right? From here, if you can actually break down your problem into subproblems, the next thing that you're going to do is potentially, this isn't always true, is you're going to do something called guessing. Sometimes you don't have all your information, and we're going to talk about one of those in a little bit here, but you are going to find cases where you need to make an educated guess on how to actually go forward or which direction to take the algorithm next. So it may not be obvious at first, but guessing is something that can be very critical, and sometimes you can use informed guessing. And the third one is, how did I word this? So it's relate subproblems So we've potentially wrote an algorithm, we hopefully at this point wrote an algorithm that has broken out the code into smaller chunks of things that need to be solved. At some point, we need to understand how those smaller problems come together, how they are actually related to each other in a way that actually creates the final solution. So that's what relate subproblems is really about. To do that, we use, let's see, we're gonna call this recursion or recurse, and then memorize. All right, so we know what our subproblems are. We potentially have performed guesses in our logic on which direction to go or which item to solve next. We know how to relate our subproblems back. We utilize recursion and memorization. Remember, if you remember, memorization allows you to prevent, especially if your subproblems are defined well, it allows you to prevent from duplicating your subproblems over and over again. And the fifth one is really just solve or like complete. So if you ever get stuck, the first thing to do is think about where you are in this scenario, and it actually you typically find that people get stuck in this one, right? You can normally figure out what your subproblems are. It's a lot of times hard to know if you're going to be choosing, this path or this path in a scenario. So guessing is something that's actually quite important. All right, so let's jump into the shortest path example. All right. So let me give you an example here. So let's imagine that we have a path that looks something like this. All right. And potentially we have other edges, right? Maybe right off the root here. And let's call that V over there at the end. If we needed to find the shortest path from S to V, we could use a form of dynamic programming to actually accomplish that. So, we're going to start by using a tool that we talked about in the 5 steps, guessing, right? So we can actually say that DP is equivalent to recursion plus memoization plus guessing. So those are the 3 things that I like to think about anytime you're doing a dynamic programming problem. So what do? You try everything. You guess at a solution and you pick the best one. So in the scenario of shortest path, we're going to look at all the locations from S that S can go. And because it must be one of the edges going out of S, then we can recursively keep doing this. So for example, we could travel down this one and we never get to S. We never get there. We maybe travel this one, right? And again, we never get there. Then eventually we go here and then we check all the edges off of this one, which eventually leads us to this one, to this one, to this one. And now we've iterated over all the possibilities of the path. And at that point we know which one is the most efficient because there could be more than one. This is called the first edge approach. And another way to actually do that is looking at the last edge. So what if you went and started, there could be multiple edges here, for example. What if we started at the end in that case? It's basically this, you're going to end up with the same concept, and you're going to be following this out recursively until you get to S. That's called the last edge approach. How do we calculate the overall, which one is the minimal? Typically what you're going to find is these lines are going to have some sort of weights on them. And as you're traveling, you're going to be able to find the minimum weight to get to from S to V. This could be the distance. It also could be some sort of difficulty. It could be any number of scenarios that you're going to use in programming, such as even something as far as length of characters or height of locations or maybe traffic. Any number of things like that could actually affect it. So we look at this, and if we had a graph that's just gigantic here, let's imagine these things go out forever. Just a really massive, absolutely massive graph here. We're going to end up having to do a lot of work to actually find the actual path, the shortest path. So it's not very efficient. Alright, so what can we do with memoization, right? We can make it better with memoization. And how do we do that? The first thing that we want to do is, let's think about it from this scenario. If we've calculated a path already, for example, let's say that we've got, let me erase some of this, make sure we can read that. So, let's say that we build a table. So we've got this table that actually stores, so S to V, right? And then this will be the value. And that value is probably the combined weight up to that point. Depending on your algorithm, it could be a couple different things. So what do I mean by S to V? S would be our starting node. And maybe V is actually a node that we're currently visiting, right? So the visiting node. So let's say, for example, especially if we end up with loops, a loop would be something like this, right? We've got that to that. So those are a couple cycles that are actually in there. They're called official cycles. So let's say we're here, and we're looking at this node now. This node, potentially, so if we were to call this the starter, maybe this is 1, 2, 3, 4, 5. So if we were to look at S3, we should have a value here of something, if we've already calculated it. So we use a lookup table to potentially keep from having to recursively go through the solutions again if we've already solved it. And then as we do recursively go through those solutions, we add those values back to the table so they can be looked up in the future. I'm going to give you an example though that's kind of interesting. So just remember this table that we've got here to the right. That's important to keep in mind. So we're going to use this undirected, and then I'm going to add some direction back into it. So from SB, if we look at this as undirected, for example, we could actually go back to S again. So what does that end up giving us? That gives us SS. And you're going to probably start to see the problem here. Now, we also get SB here. Alright, so what ends up happening is this becomes basically an infinite algorithm. And like I said, there are ways to fix it, and it really wasn't the greatest example. It can be mimicked with the directions. But if we did make these unidirectional, like where these edges were to go correctly, we could prevent that. And that is called a DAG. So what ends up happening with DAGs, we can end up getting directed acyclic graphs. So those are graphs with edges that actually can only travel one direction. And we can actually get pretty good performance on a DAG because now we don't risk looping back through already solved, especially in the brute force case. And if you've ever heard the term depth first search, this is very much what a depth first search is doing from that. So how do we fix this problem here? We basically we make it acyclic. We make it so that it can't have cycles in it. And we do that very much with what I had before. So this would go here, and then so this one would go here, that one would go there, and that one would go there. So now we've taken a cyclic graph and turned it into an acyclic graph. So we almost have to take it a step forward, especially in graphs that potentially have cycles. It's very easy with this type of algorithm to end up in an infinite cycle. And the only way to really get around that is to do by turning it into a acyclic graph. Alright, so let's talk about if we were to look at a couple other quick problems here. One of them that's actually one of my favorite. And this one, I mean, just so you know, graphs and graph searching is very important. I would highly recommend, if you don't understand this, maybe watch this again, and I plan on doing a little bit more in depth closer to the end of the class. But I want to talk a little bit about another pretty cool use for dynamic programming. And one of the things I'm going to challenge you to do is to take a look at what you think a proper mechanism for guessing would be in this scenario. So let's look at text justification. So let's say that in Microsoft Word, for example, you type a big paragraph, you've got all these, maybe that's a long word, and you want it left aligned and right aligned, so justified. You want your text justified so that it matches up, it looks pretty, and you don't end up with a huge gap like this, right? That doesn't look good. The greedy approach to this is fit as much as you can into the top row, do the same in the second row, do the same in the third row, do the same in the fourth row. But what ends up happening in this scenario is that, especially in a case where you end up with a small text and a long text, you can end up with these very large gaps that would have been more efficient had we done different placement through these rows. For example, especially with this big gap, I'd be willing to bet if we were to run this more efficiently that we can make these more evenly spaced, right? Why does the first row look nice and the last row look bad? So how can we take that greedy approach, which is not optimal, and make it better? And that's really where dynamic programming comes in. So let's start thinking about what the subproblems are. The subproblems are let's just talk through the scenario here. What are we looking for, right? We are looking for optimal placement on every row. We're not looking at just a single row. We want optimal, and the words that they use is actually, we want to optimize badness. So a badness would be higher if there's more space here. So we want to optimize badness. So I'm going to write badness up here. And how do we calculate badness? The badness of a particular row, so let's make this row. The badness of a particular row can be counted as total width. So if we were to look at this as total width, and minus the actual used characters. So what does that mean? It's like, what is the width of this plus that plus that? So minus used, and then they cube it. That way it exasperates the badness, right? We're not 100% sure why they cube it. I bet you a squared would work as well. It's just part of the algorithm that someone has created over time. But what it does do is, as this number gets bigger, when it becomes cubed, it gets even bigger. And I think that's important to keep in mind because when we were to look, if we were to look at this, for example, this one would clearly have a higher badness score. Right, so this would be higher, and this one would be very small. So over the entire like paragraph, or over the entire body of text, we want to minimize badness. So our subproblem is, one of our subproblems is, I guess I would say that we need to figure out the optimal badness per row. But to do that, we've got another problem to actually solve. And that is, how do we know what text goes on what row? So if you were to think about it in a very simple term, and we go back to guessing, ultimately what we are going to be doing is we are going to be guessing whether a word starts at the beginning or not. That's really what we're looking at. We do know without a fact, for a matter of fact, that the first word is going to start at the very first of the paragraph of the body of text that we're using. So how can we use memoization? Think about how we did graph navigation. And if you were to think about it from the standpoint that we only have two options here. You either start or you don't. You either start the new line or you don't start the new line. And we can build a memoized algorithm to do that. So if we were to actually take text from here, we know that this one is going to be one that we start with. But we go here and we say yes or no. Let's try both of them. We try going down the route of it starting a new line, and we now have a badness score for that scenario. And if we do that, what ends up happening here? We can recursively generate a very nice graph based on a very simple yes-no. Is it a new line or is it not? And if we get to a word that doesn't fit in the current row we're filling, it becomes an automatic yes, right? Because we know that that has to go down to the next line. So with that said, I think we'll end it here. Hopefully this has been really helpful, and hopefully this format is a little bit nicer than doing it on the computer. But overall, dynamic programming is going to carry into part 3 on Friday, and then we will be talking a little bit more in detail about some of the complicated use cases for dynamic programming. And I've got a pretty cool assignment that I'm putting together. I don't have it for you guys this week, but I will have it for you either on Friday or early next week. I would like you to just think about text justification as a whole, and as a fun exercise, feel free to try to implement this. This would be one that I think would be absolutely a blast to implement. And there are some really cool resources out there that can give you some ideas on how to approach the problem, some of the problems that you may have. But I would feel that I've given you enough here to actually create a memoized dynamic programming solution to text justification. And a fun thing may even be to create a greedy algorithm version of that first. Alright guys, and I hope you guys have a great night, and I'll see you guys next time.